All right, so right now I'm going to tell you a little bit more about the reaction coordinate diagram to answer some of the questions you all had at the end of class. All right, so this is our reaction coordinate diagram, where we have the reaction of a substrate turning into a product where the enzyme isn't involved. So in this case, we have the enzyme plus the substrate, the enzyme plus the transition state, which we can represent as the S double dagger. So when the book asks you to talk about the different forms of the substrate, it's merely talking about the substrate or the transition state. So I often write the transition state either as the TS double dagger or just as double dagger, but sometimes books will write the transition state as the substrate double dagger that indicate that the transition state still looks like the substrate. Now, what happens when an enzyme catalyzes the reaction? So this is a case where either for some reason the enzyme isn't interacting with the substrate, either because it's the wrong substrate or maybe it's on a protest, I don't know. But when the enzyme actually interacts with the substrate in the transition state, this is what happens. We know that the enzyme doesn't affect the start or the end state because the starting state is still the enzyme plus the substrate, so the enzyme not being bound to the substrate, or the enzyme being bound to the product because the enzyme's not bound to the product because it's kicked the product out. But we do know that the enzyme affects the transition state. And in fact, we know that it lowers the energy of the transition state. Now, here I'm drawing this as the enzyme dot S double dagger because this is indicative of the fact that the enzyme is bound to the transition state, and it's going to form interactions. Specifically, it's going to form interactions such as non-covalent interactions such as hydrogen bonds or salt bridges to anchor the transition state into the pocket of the enzyme. And so if we were to go ahead and to compare the activation free energies, so this would be the delta G of activation uncatalyzed versus the delta G of activation or catalyzed, we would see here that it would lower the delta G of activation, which would make it, and if we lower the delta G of activation, that means the rate of the reaction is going to increase. Now, that isn't the only thing that happens. We know that the enzyme that to lower the energy of the transition state, the substrate, the enzyme has to be complementary to the transition state. However, the enzyme actually does still bind to the substrate because it has to bind to the substrate before it joins the transition state to make sure the chemistry can happen. However, it just doesn't bind the substrate quite as well as it binds the transition state. And so one way we can see this is by saying that the delta G between the enzyme plus the substrate alone and the enzyme substrate complex, or the delta G ES, is smaller than the free energy difference between the enzyme and this transition state when they're not complexed versus the energy of the enzyme in the transition state when they're complexed. So the binding of the enzyme to the transition state lowers the energy of the transition state more than it lowers the transition state of the substrate. Now that may be a little bit confusing for you still. So if you're still confused, we're going to think about it in a different way. So let's say that we have a case where the enzyme really, really likes the substrate. Oops, get rid of that double dagger because that's the substrate. So let's say the enzyme binds the substrate and it likes the substrate more than it likes the transition state. So the delta G E plus the delta G ES is going to be greater than the delta G ES double dagger. What does that mean practically? Well, we erase those. What happens is if we compare the old delta G of activation for the substrate to the transition state on its own versus the delta G activation for the enzyme substrate complex, we see that if the enzyme likes the substrate too much, the activation energy can actually become bigger than it was before. All right, so we don't want the enzyme, we want the enzyme to like the substrate just enough that it can pull the substrate into its active site, but we don't want the enzyme to like the substrate so much that it gets harder to make the transition state. So we want the enzyme to be complementary to and to bind the transition state enough that it lowers the transition state to a degree that it's still easier, but we want the enzyme to like the substrate enough and be complementary enough that it lowers it a little bit, but not enough to counteract or undo the stabilization of the transition state.